Okay, thank you, Manjari. So in Beijing now, it is in the evening, but in your place it's the afternoon. So I'm talking about the roadmap map to Strange Star. Actually, this is my second time of video talk to our Indian friends. A few years ago, in 2016, we tried to organizing a meeting relevant to Asia SKA sciences on neutron stars. Unfortunately, I cannot. I could not go to Goa for this talk, but I just present a video talk. So this time, this is my second video talk to our Indian friends, and I hope in the future I could be for my third talk. This it should be a real talk and not a virtual or video talk. So actually, both the talk a few years ago and the talk today are related to a compact star. This is a very big problem. You know, for an involved massive star, the core of the star, become the nuclear energy released. So there is no actual free energy to release, so that there is no enough pressure to be against the gravity. So at that time, normal baryonic matter should be squeezed very extensively, very strongly to form a so-called Chandra nucleus. A Chandra nucleus. That means normal atomic nuclei become closer and closer contact to each other. Eventually, we have a matter with density around the nuclear density, or even higher than the nuclear density because of gravity. So this is this is the so-called compact star or neutron star or a pulsar, manifested as a pulsar. But the simple question is actually not so simple. But the real situation is that we do not know the real answer. But we try to know the answer, to try to know the nature of the gravity compressed baryonic matter, because the central residual compact object, the physical behavior of the residual compact object is related to the many rich astrophysical phenomena. For instance, pulsars, gamma ray bursts, FRB, fast radio bursts. This is a very hot topic of FRB. You know, this is a process of supernova and many others. For instance, the nuclear synthesis, neutron star, binary neutron star merger, nuclear synthesis. Anyway, all of these rich high energy astrophysics phenomena relate to the nature of the compact object. This is a very interesting and a big problem, but not solved, remains puzzle. So today I try to show you the I should be the tourist. I act as a tourist guide to show the park This is a part of gravity compressed baryonic matter. In the central core of the massive involved star becomes squeezed so that atomic nuclei contact each other, eventually have a compressed baryonic matter. This is a part of the gravity compressed baryonic matter. And I should be this afternoon, I should be as 1 hour, I should be a tourist guide to show interesting building in this park, and to show the way to the interest building. I should told you 2 ways to, for instance, this way to very fantastic building of neutron star, and this way to some buildings of so-called strange star. So as a guide, tourist guide of this park, let me go ahead. First, I should explain to you why we should kill electron. Why we should kill electron? There's a panel just in front of the park door. So why? So first I explain why we should kill electrons, so that we have only 2 ways. So this is very simple, but the history is long. The real history was from Landau in the beginning of 1930. Landau published a paper, and this paper was considered as origin of neutron star. Landau addressed in his paper, we expect, that means after core collapse, I means if the star, the core mass is higher than Chandra-Sekhar limit. This is Chandra-Sekhar, you know, this is very famous Indian Chandra-Sekhar limit. So the electron pressure is limited. If the gravity is so high, that means the mass of the star is higher than a limit. The gravity is high, then electron pressure cannot stand against the gravity. So Landau think about this. So after the collapse of the core, he wrote, I may read this sentence, very important sentence. We expect that this must occur when the density of matter becomes so great that atomic nuclei come in close contact, forming one gigantic nucleus. This is a very original idea. Later, eventually developed to neutron star. Landau talked about the giant nucleus, but he didn't show the scale of the giant nucleus. So how large is giant? I mean, you know, our normal atomic nucleus, the scale is only a few firm meter. So if you try to form a giant nucleus, why giant? What kind of nucleus is giant? I should say that the scale could be compared, if we call this nucleus is joint, that means the scale of the nucleus is larger than a typical or order magnitude scale. This order magnitude scale, we call this as quantum variance. You know, quantum variance is about 1 or 2,004 meters. So usually for normal atomic nucleus, this is a small nucleus or microscopic nucleus. So if a nucleus forms after supernova co-collapse, the scale should be much, much higher than this quantum scale, quantum variance. So we call this as joint nucleus. And also we can estimate the typical or critical baryon number as this the cubical of quantum variance divided by cubic per meter is around 10 to 9. So usually the most highest number of normal atomic nucleus is around 300, just 10 to 2. So 10 to 2 is much smaller than 10 to 9. So this is a small normal nucleus, not the so-called joint nucleus proposed by Landau in 2013 too. So let me have exercises to squeeze an apple. You know, apple actually is atom matter, atom condensed matter. So the basic unit of apple is atom, and the atom is composed by nucleus and outside electrons, and the basic unit inside the nucleus is proton and a neutron, only nuclear, and the mass difference between neutron is heavier, a little bit heavier than proton, is about 1. So this is apple. So we try to do an exercise to squeeze this apple so that atomic nucleus close contact each other. Eventually we have a nuclear density matter. Nuclear. So let's do this exercise. We can estimate the apple total baryon number is around 10 to 26 because you know the typical mass of an apple could be 100 gram divided by mass unit 10 to minus 24. So we have the apple baryon number could be 10 to 26. This 10 to 26 is much higher than this value. So you eventually have a joint nucleus proposed more than 80 years ago by Landau. You know, this is not easy because there's a Coulomb repulsion between atomic nucleus. So this is very difficult to do. But in the inside the massive core of an involved star, the gravity is so strong, dominate all of the other forces. So we are very difficult to squeeze this apple. But gravity can squeeze all of the core inside an involved massive star to finally have a compact object with at a nuclear density. Yeah, that's so. Anyway, the total baryon number for core-collapsed supernova remnant compact object, the baryon number, total baryon number, is not this value for Apple, but it's around 10 to 57. I mean, the residual compact object of involved of the core-collapsed supernova remnant is the baryon number is around 10 to 57. It's much higher than this Apple baryon number. But anyway, both the Apple nuclear matter and core-collapsed remnant, both this matter object could be considered as giant nucleus. Giant. That's because in both cases, the baryon number is much higher than this value, this critical value. So, and if we can before squeeze the apple, electrons outside an atomic nucleus is non-relativistic. But if we squeeze the apple to be in the nuclear density, so we have giant nucleus. You can calculate, and you finally have the scale of the remnant nucleus is around 50 micrometer, and the density is around the nuclear density. And if electrons do not convert to others, I mean, no weak interaction, electron keeps there, and you can because the volume becomes so small, rather than 1 meter for normal apple. So the electron density become higher, and you can calculate the kinematic energy of electrons could be around 200 MeV. This is extremely high density. You know, the mass difference between neutron and proton is about 1 meter. So this 2 orders higher than these differences. So this fact actually motivated Landau to think about the keening electrons, and as I told you, for core-collapsed supernova, because gravity is not free. If you squeeze an apple, gravity free, but for core-collapsed supernova, the gravity dominates. So the density could be higher than nuclear density. And the baryon number is not 10 to 26, but 10 to 57, as I told you. So for core-collapsed supernova remnant, 2 uncertainties were popularly discussed in the literature. Quarks deconfined or not, or confined or deconfined, or is there strangeness significant? So this is 2 uncertainties. Let me go this way. You know, neutron and proton are 2 flavors of quarks, up and down quarks. So actually, in the year of Landau, there's only at that time proton and neutron were considered as elementary particles. So they can only think about the conversion of electron and a proton. No other ideas. So if you go in this up and down two flavor way, finally you go to the neutron star building. Let me show you. This is very simple. Let me, okay. Because these very energetic electrons. So if electrons keeps there, then the kinematic energy of electrons or Fermi energy of electrons could be around 200 MeV, as I told you. So if electrons and protons connect each other to finally to form a doublet, at that time, no weak connection. I mean, there's no idea of so-called weak induction. Later, we know this is a weak induction to convert the proton and neutron. But in Landau's time, Landau just think about a close bonding of proton and neutron to form a doublet, as proposed by Rutherford. So, and this doublet later renamed neutron. And we then call this action as weak induction. So weak induction can convert a proton to neutron because of the energetic electrons. And finally, we can have a lower energy of the system. This is very simple. So if you just think about the two flavors, up and down, this weak induction is equivalent to the level or quark level conversion. Up quark is converted to down quark. So this is two flavor cases. So we call this conversion as neutronization. So after neutronization, finally we have lower energy of the system and more neutrons than the protons. And in the I think most of you know this. But the situation is not so simple because, you know, neutron should decay in vacuum. So if you try to have free neutron, you have to have you have to forbid free electron, free neutron to proton. You forbid neutron decay into proton. So you have to have very high density. So in the near model of a neutron star, there's a crust. Outer crust and the inner crust, the density become higher and higher. The neutron, the electron density become higher and higher consequently. And finally, a neutron is forbidden to decay into proton. So you have uniform nuclear matter. But it is frankly to say that we are not familiar with most inner part of the neutrons. Maybe there's free quarks or hypons or other kinds of matter. So this is a very popular model of neutron star. I think most of you know this. Anyway, let's think about another way. You know, in the 2060s, the standard model of particle physics developed, and we now know the quark flavor. The total number of quark flavor is not 2, but how? But 6. And the proton and neutron are not fundamental particles. Quarks are the building block of proton and neutron. So this 2 flavor way could be questionable, and they actually, you know, in the standard model of particle physics, we have totally 6 flavors of quarks. But you may ask me, why you consider only 3 flavor cases, not 6 flavors? This is question. I first explain why we are focused on 3, although we know there are 6 flavors, totally 6 flavors of quarks in the standard model of particle physics. The reason is very simple. Because the energy scale for relevant to our cases is not so strong. It's around 0.5 or 0.4 GeV. You can, yeah, you know, for the remnant of co-collapse supernova, the typical density is around the nuclear density. Because of gravity, the density could be higher, a few times nuclear density. So in this case, you can estimate the energy scale of this kind of dense matter by the so-called Heisenberg's uncertainty relation. The separation between quarks could be around 0.5 meter. And the energy scale could be delta P C. So you can estimate the energy scale H bar C over 0.5 meter. You can finally eventually have an order of magnitude value for the energy scale of dense matter related to our cases. It's around 0.5 or 0.4 GeV. You know, for heavy flavors quarks, charm, bottom, or top quarks, the rest mass is higher than 1 GeV, is more heavier than 1 GeV. So in this case, heavy flavor of quarks could be forbidden. We can only think about 3 flavors because the risk mass of strange quark is higher, although the strange quark mass is higher than up and down. This up and down quark mass is out of MeV or 10 few MeV, but the strange quark mass, risk mass is around 100 MeV. So it's high, it's massive. Strange mass is massive than up and down quark, but this strange quark mass is much smaller than the energy scale of our dense matter. So strangeness should be very significant when we try to answer the nature, try to solve the equation state of dense matter of after a co-collapse supernova. So actually in 1980s, many famous people are discussing this possibility of strangeness in dense matter at a supernuclear density. For instance, in 1964, Edward Witten proposed that strange quark matter could be in bulk, could be in the absolutely stable ground state, because the likely Fermi momentum of if quark are free, for quark matter could be around 400 MeV. So more than the a few hundred MeV firm energy is more than the strangest quark, strange quark mass. So it could be energetically favorable for some of the non-strange quark, UD quark, to become strange quark, and eventually we have a lower energy of the system. This picture could be very show the very straightforward way of this conjecture. Later we call this as so-called Witten's conjecture. And if there is only two flavors of quarks, then the Fermi energy could be around 0.4 GeV. But if you have another degree of strangeness, and then there are three flavors of quarks, and finally the Fermi energy could be lower down to have a lower, more stable, strong matter state. But this is in the regime of free quarks. As I told you, if you try to answer the very simple question of the nature of co-collapse supernova, the compact object, you have to think about the 2 points. One is strangeness, significant or not. Another issue is about confinement or deconfinement. So for free quark case, you suppose the interaction between quark could be weak decoupling, so that the quarks could be in a free state, free quarks. But this could be very questionable, because as I told you, the typical energy scale is around 0.5 GeV. I think most of you know. If you try to solve a problem in the regime of perturbative quantum chromodynamics, perturbative QCD, at least the energy, the scale energy could be higher than 1 GeV. But in our case, the typical energy scale could be 0.5 GeV. That means in our case of the dense matter, the quarks could be, the coupling between quarks could still be very strong, so that the interaction between quarks cannot be negligible, and this free quark state might not be the real situation. So this should be rejudged. So in this way, we have this building, as I told you, for free quarks. But there is another small buildings, small holes in this way, so-called Strangeon star. Let me explain this this building, this house. So at a few nuclear density, it could be questionable for free quarks. Actually, in 2009, in CSQCD 2, at the Kavli Institute for Astronomical Physics, KIA, we have this CSQCD meeting, the second CSQCD meeting in Beijing, in our campus. We have a KIA in our campus. At that meeting, I was talking about so-called quark cluster stars. Later, because there's some in order to avoid some misunderstanding, we later renamed quark cluster to Strangeon. So quark cluster equals Strangeon. What is Strangeon? Strangeon is sometimes something like a nucleon, but with strangeness. You know, our nucleon is two flavored. If we have also a nucleon like particle, but with three flavors, we call this kind of nucleon cannot be proton and neutron, cannot be simply neutron. We call this strange nucleon. And we doubled this a new word, Strangeon. We call this Strangeon. This is exactly the ideal I show in CSQCD 2, 2009 quark cluster. The reason is if you introduce color coupling between quarks, then the interaction between quarks at a few nuclear density could not be negligible. Even the interaction between quarks could be much higher than the Fermi energy of free quark matter. So that means a free quark matter state cannot be stable, so that quarks could be grouped together to form quark clusters. We call this kind of quark clusters as Strangeon. And later we show that this kind of Strangeon matter state is very steep. Is welcome by later observation. So let me okay. So we have two kinds of ways to kill electrons. As I told you, if you think in the way of two flavor, only neutronization to kill electrons. But if we think there are three flavor way, in a three flavor way, in this case, Strangeonization can also effectively kill electrons to have a stable state. So I show this cartoon from core-craft supernova and normal atomic nucleus become closer and closer to eventually have a nuclear density matter, and the electrons becomes energetic, very extremely energetic. You know, we have two ways to kill electrons. For the two flavor case, we have only neutronization. convert proton to neutron. We have finally neutron star. I show you. But there could be another way. Quarks are all still localized in a nuclear-like particle we call Strangeon. So Strangionization is very similar to neutronization, but only from 2 flavor to 3 flavor. And from a symmetrical perspective, you can see neutron star is 2 flavor, but very asymmetric of 2 flavor of quarks. The asymmetric values, dimensionless asymmetric values delta could be higher than 0.5, 0.8. But for strange quark matter, and Strangeon matter, the both these 2 kind of strange star is in the regime of are in the regime of 3 flavors. So the asymmetry, dimensionless symmetry factor is negligible. Could be lower, smaller than 10 to minus 4, or even smaller. So from a symmetrical perspective, strange star, either strange quark star or Strangeon star, could be more beautiful than neutron star, because the because in these 2 cases is symmetry, but for neutron stars is very, very asymmetry. If God allows symmetry, then maybe he should choose strange star, either quark star or Strangeon star. Anyway, I may have this summary: neutronization and Strangionization in the standard model of particle physics. So for neutronization, you know, as I told you, totally in the standard model of particle physics, there are 6 flavors, but for 3 heavy flavors quarks forbidden. And for this 3 flavor of light flavor quarks, neutronization and Strangionization, quarks are not free in both cases. So how can we model Strangeon matter quantitatively, not only qualitatively? I think we can think about a so-called linked back model. This is a not new model, but proposed long times ago by our Chinese colleague in our campus in Peking University, Professor Zhang. He now is he was retired more than 10 years ago, but still he's think about a very interesting science. But in 1992, he published a paper on so-called MIT back crystal model for nuclear matter. This model is very not so easy to calculate, but Professor Zhang did this. For our case, we can use a simple version of this back crystalline model. And just today, we put our calculation on archive. You can see this archive number to download this paper. We just present a simple version of back crystalline model or linked back model. We have the total energy of quarks and electron cell quarks and vacuum, long perturbative vacuum energy, and even the zero energy, 0-point energy. And we can parameterize the model, and we, in our case, we have 3 parameter model, so-called C1, B2, and B3. We expand the back constant for hydrogen, expand by asymmetry of this value. Chi is a symmetry value. So this is if there's we think if we have a stable 2-flavor nuclear matter, this B1 could be 0. So we have this 3 B2 and B3. Also, this C1 is related to the normalization, 0-point normalization value. And these 3 parameters were collaborated by these 3 observations for nuclear matter, for our normal nuclear matter. The nuclear saturation density, the bonding energy of nuclear, and even and also the incompressibility, K. These 3 observational values. I mean, we choose these 3 model parameters to reproduce these 3 values for nuclear matter. Then we extend this model to 3 flavors, and finally we show that Strangeon matter could be more stable. This is for 2 flavors, and this is for 3 flavors. It could be more stable, and we can also calculate the mass radius curves for Strangeon matter 3 flavors and nuclear matter 2 flavors, and also calculate the lambda 1.4 tidal deformability. For our Strangeon matter, this lambda 1.4 is smaller, but for 2 flavor models, some of the models could be ruled out by the mirrored tidal deformability of GW170817. So this is our model for Strangeon matter. Actually, more than 10 years, we are focusing on the astrophysics, try efforts to find evidence for Strangeon star, either from global cases or surface situation. I may show a phenomenal, very detailed astrophysics, but I think I do not go to very detailed so-called drifting subpulse. This could be evident for Strangeon matter. This story now is related to the most biggest, I mean the biggest single-dish telescope, Chinese FAST. Our Indian people are more than welcome to join the FAST observation. And I'm happy to tell our Indian people that FAST should be open to all the scientists over the world from the next year, 2021. So, so you are more than welcome to submit the proposals. If you try to know this and you have not received this message, and you try to submit some proposal for fast observation, please email me as early as possible, and I may send you, or later I may send you the message for submitting fast proposal. And this evidence for Strangeon star by the drifting subpulse observation is related to this fast observation. This is a very old story, Ludman-Sosnan model. This is very popular observation for the drifting subpulse. But because fast, the sensitivity is extremely high, and fast can observe many different kinds of drifting modes, very weak modes of drifting subpulse, and show that this so-called P2 and P3 correlated. This is P3 and this is P2. I'm sorry, because of the limited time, I may not go to very astrophysical details. Just to show you that there's a very nice correlation between observed drifting subpulse P2 and P3 by FAST. And this paper was published last year, the early science of FAST. And you can easily understand if there's different, I mean, just on the surface of a pulsar, the surface E parallel is not the same. If you have very different kind of E parallel, and then you can have different kinds of modes of drifting subpulse. But why? How can we have different kinds of E parallel for I mean in the neutron star model? For the older I mean conventional neutron star is a very smooth surface of neutron star. It's difficult. You can hardly have different kinds of E parallel. But for our Strangeon star, if the surface is not smooth but a rough surface, then you can have you may have some place you have a higher E parallel, some place at another place you may have a smaller or weak E parallel. Then you can have different modes of drifting subpulse. So the correlation of drifting period P2, P3 could suggest a rough surface of pulsar. And the bonding energy of particles on the surface need to be very high. If there's Strangeon, because Strangeon matter is a strong matter, so there's there may be a small hill or small mountain on the surface. So different place may have different values of E parallel. So we then can have different modes of drifting subpulse. This could be a hint for the existence of drifting subpulse. Anyway, I hope our Indian people can submit a proposal to research further by FAST next year. I may stop after this brief summary. Many people are interested in black hole because, you know, GR, general relativity, was proposed by Einstein in 1950. So around half century, so black hole physics, astrophysics, become very hot, very popular astrophysics. But, you know, the standard model of particle physics was developed in 1960s. So half century later, exactly now, neutron star science or neutron star physics become hotter and hotter. And this could be a very important problem in this way, essential, especially in the year of the multi-messenger astronomy. If GR is reliable, then we may solve this equational state of neutron star. You know, neutron star could be a general idea, either conventional neutron star or our strange star. So this equational state could be finally solved just in our age. I hope this brighter future could be could help all of our audience. So in this talk, the basic unit inside a pulsar-like compact object, I propose could be the basic unit could be Strangeon rather than nuclear. The difference is only 2 flavors, 3 flavors. And we have many observational evidence for Strangeon star. And in the future, I hope we can find more evidence evidence for strange star or Strangeon star or others. Thank you very much, and we can discuss about any questions related. Thank you.
Thanks, Renxin, for this awesome talk. We have learned a lot about strange stars and strangeons, and thanks for mentioning about FAST and inviting us to apply for time. I know FAST is really awesome. Probably others you will also like to know. Even in the trial run, it has discovered a good number of millisecond pulsars. So it is really an amazing instrument, and hope it will contribute a lot in our understanding of equation of state to the general relativity. So now I think let us go to the questions. So I see there are 3 questions. So first from BC Paul, for a strange star, how far it is correct to consider MIT bag model? As B in the MIT bag model may be a variable function of R in a star rather than a constant.
You mean the MIT bag model for strange quark matter?
Yeah, so the question is whether it is okay to take the bag parameter B as constant, or whether it is better to take it as a function of R, I mean radius inside the star.
For quark matter, the bag radius is a strange star radius.
Okay.
I mean, this for conventional MIT bag model of quark star. Usually we treat the B as a constant. But for our case, so-called linked bag model, I show you the bag. In our bag is not 10 kilometer, but only order of 4 meter. So maybe 1 or 1.5 ferrometer radius. So, but these bags, I mean, all of the bags are linked. So there are 6 windows for a certain bag. 6 winners cut it. And all of these bags are linked together. So in our case, so-called back-linked model, this back value is not constant. Changes as a function of chi, density or the flavor. So and we have these two free parameter, and even their normalization value, lambda is C1, something like lambda, conventional back model. So we have 3 free parameters, and we can parameter these 3 values to reproduce the observation of nuclear matter of our normal atomic nuclear. I'm not sure if I can, if I have answered your question.
Yeah, I think it was well explained, and if there is any further comment on this, probably there can be email communication, because we have a few more questions. So second question is from Prashanth. What is the typical baryon number at which you claim to form strangeons? Is the surface tension of quark matter taken into account in your calculation?
In this calculation, show this archive paper, we have not considered the surface. We just consider infinite Strangeon matter. We have not considered surface. This surface is, I mean, this surface and also the curvature is related to this surface, this back surface. But the Strangeon matter have no surface. This small back have surface. We consider this small back surface also the curvature of small back. We just consider Strangeon matter infinite Strangeon matter. Linked, I mean, all of this, all of the backs are linked by these 6 cutted windows, infinite.
Thanks, Renxin. So okay. The third question is from Paul Lasky. The mass radius predictions for your Strangeon Stars looks in tension with the nicer results discussed yesterday. How much room is there for the radius at fixed mass to increase with your model? Is it possible to have hybrid stars with larger radii?
We just consider Kinnear observations. That is, I mean that I mean dynamical by dynamical effect. You know, it's I mean gravitational wave observational constraints for lambda 1.4. This is dynamical observation. And another kind of dynamical observation is so-called measurement by pulsar timing, massive pulsar, 2 solar mass massive pulsar. As for the observation of LISA, yeah, this is observation, but I think it's very model dependent. You know, there's many, you know, the surface of the pulsar object could be very complex. Dipole, multiple field, conductivity, hotspot, seat, or the shape of hotspot. It's very complex. So very, I think it's very model dependent. But anyway, mass measurement and dynamical lambda 1.4 are very interesting and very essential to constrain the mass the equation state. Okay.
Hi, actually, we are running little out of time, but there are two more questions, but I think we can quickly discuss those. So first question is, given the present sensitivity of advanced LIGO or Virgo, is it possible to distinguish between Strangeon star merger and neutron star merger, and what differences are expected?
Yes, good point. You know, GW 170817, yeah, it's the first event of binary neutron star. So in the, and also very nearby. So we are lucky. We are very lucky. You know, this CSQCD meeting in India is also as a ceremony of, I mean, the 3 years anniversary of discovery of GW 170817. This is very lucky, and we are very happy to know this. But in the future, I think if we have, if we can discover more binary neutron star merger or binary neutron star black hole merger to constrain effectively the lambda 1.4, the tidal deformability. This could be a very precious observation to constrain the equation state. For instance, how large is lambda 1.4? For if this lambda 1.4 is around, I mean, is around 200 in this yellow bar is this region, this region, then the two flavored neutron star could be ruled out, because this two flavored neutron star, lambda 1.4 of this two flavored neutron star could be much higher than, much larger than 200. So could be the model could be two flavored model could be ruled out, conventional neutron star. So this could be very interesting in the future. Anyway, if in the future we constrain lambda from the 1.4 in this region, I mean 500, then our three flavored Strangeon star model should be ruled out. I will be really sad about this observation.
Thanks, Renxin. Although we are already 7 minutes out, but let us take one last question, because this will always encourage students to ask questions. So the last question is from Rudrapriya Das. How do you measure asymmetry in Strangeon star and neutron star?
The asymmetry of nuclear matter or neutron star, I mean infinite nuclear matter, equilibrium by weak induction. You should have more down quark than up quark, or equally more neutron than photon. So this data equals the number of d quark minus the number of u quark divided by the number of d quark plus the number of d quark. So could be larger than 0.8. Its asymmetry is higher. For strange matter, because if there's a beautiful symmetry, that means UDS, the number of UDS quarks are the same, perfect symmetry, perfect symmetry. So data should be there. But you know, during in order to keep the chemical weak action, chemical equilibrium, because of massive strange quark, I mean the mass of strange quark is larger than the masses of UD quarks. So the number during the in the chemical equilibrium, the number of S quark should be smaller, a little bit smaller than the number of UD quark. So this data is calculated by the number of U quark plus U quark plus D quark, the number of D, we name the number of U quark NU plus ND minus 2 times NS divided by NU ND and plus 2 NS. So this value is very, very small. So we have this almost a perfect symmetrical case for strange, either quark matter or strange matter. Okay.
Thanks, Renxin. So thanks again for this awesome talk and explaining all the questions so nicely. So let us all thank Renxin again.